All right, welcome back. Welcome to this lightning talk session. Our first talk is by Ludovico Lami. Take it away.
Right, thanks everybody. Welcome back. So, okay, the nickname of the paper I'm going to present now is Die Hard Quantum Communication, and you'll see why in a moment. So this is done in collaboration with Martin Plenio from Ulm, Vittorio Giovannetti in Pisa, and Alexander Holevo in Moscow. Right, so the main topic there that we want to tackle here is the set of general attenuator channels. So just a brief recap. This is, the same channels I talked about yesterday, actually. So your incoming state rho, will be your signal, is mixed in a beam splitter, which is a passive optical element, with an environment state sigma, right? And so the beam splitter has a certain transmissivity lambda, which can be between 0 and 1, and your the output state will be a mixture of rho and sigma, right? I mean, a kind of mixture. It's mixed via the unitary transformation of the beam splitter. Okay, so why do we care about attenuators? Because they actually model actual quantum communication across physical media, right? Either optical fibers or also free space communication, say, to satellites. So the usual, for the usual typical optical cable, this transmissivity lambda will decay exponentially with the length. So, and it will lose a factor of 10 for every 50 kilometers. Okay, and the usual assumptions on the state sigma, the environmental state, are that sigma is a thermostate. Okay, this is the usual assumption. So which brings you to a thermal attenuator channel, or in the case where the temperature is 0, to a pure loss channel. The problem with this is that if you make such an assumption on sigma, then for transmissivity smaller than 1/2, that means for length larger than 15 kilometers or something, the quantum capacity of the resulting channel vanishes. Okay, so what we ask in this work is whether you can change this, you can fix this by just changing the environmental state sigma. Okay, and this kind of belongs to a wider scheme. It's called passive environment assistance. Was fleshed out in this paper by Carumanci, I think Andreas Winter, and Dong Yang and Stefano Mancini a few years ago. So their scheme is much more general. We are doing something really a bit more like a stripped down version, because it's enough actually. And so what we want to do is to maximize the quantum capacity of this object by varying the state sigma. Okay, so this is our main theorem. Let's look at it. So we consider the quantum capacity at a fixed energy constraint. So the energy constraint is fixed, say to 1/2. So that means the average number of photons you input is 1/2. And then you maximize over your environmental state sigma for a fixed transmissivity. Okay, so the resulting function, this one, depends just on sigma. And the surprising thing is that this is highly non-continuous, meaning that is actually larger than a fixed constant for all lambda between 0 and 1. 0 excluded, of course, because there you have capacity strictly 0. Okay, so that's quite surprising to me. That means that for every arbitrarily small lambda, you can pick a suitable state sigma that makes this quantum capacity larger than a constant. Okay, so you can transmit at a fixed rate. And that's really surprising, because for very small lambda, the amount of energy that goes into the output from the input is vanishingly small. And so most of the energy at the output comes from the environment, which is, by the way, also high energy in our proof. It's actually a Fock state. So this is kind of a surprising feature. That this is why Die Hard quantum communication, because for every small transmissivity, you can still make it. You can still achieve quantum communication. Okay, with that, I thank you, and I'll take any questions if there are some.
All right, thank you very much, Ludovico. I think we have to keep a tight schedule, so I suggest that if we have questions, we can ask them on the Slack. Thanks again for your presentation. Thanks. Do we want to have our next speaker maybe share their screen?
Okay, can you hear me?
Yeah, perfect. I think that so if I'm not mistaken, you have 2 lightning talks in a row, is that correct?
Yeah, correct.
Wonderful. Okay, so you can take it away and just do both at a time. That's perfect.
Okay, perfect. Well, I will try to give you an idea about multi-level amplitude damping channels and their quantum capacity. And I will start by talking about the qubit amplitude damping channel, which is one of the most simple noise models we can think of when dealing with qubits, and which basically describes how excited states in qubits decay with a decay rate gamma into ground state 0. Okay. Well, the issue of finding computation information capacities of qubit amplitude damping channel was first addressed by Vittorio Giovannetti and Rosario Fazio in 2005. And we tried to do the same thing, basically, but for amplitude damping in the multi-level settings. And the amplitude damping in higher dimensional system is constructed basically in the same way as for the qubit case. But in this case, depending on the dimensionality of your system, you will have much more decay rates possible. Okay, and to each decay rate will correspond a Krauss operator. Now, if you start playing a little bit with this kind of channel, you will see that the multi-level amplitude damping channels, MAD, are closed under composition. So composition of 2 MAD will be an MAD with a resulting decay rate given by this composition rule. You will also see that MAD can be covariant in the sense that if you have a group G and 2 unitary representations of the group on the input and output space of the channel, then this expression will hold. And in particular, for MAD, the covariance is with respect to the group of orthogonal diagonal square matrices, which are represented in this way. And the property of covariance, together with the degradability, gives you a nice and simple way to maximize the coherent information. And specifically, we'll have a maximization only over diagonal states, which is a nice feature, let's say. The point is that the dimensional independent analysis is not approachable. So we focus on the most simple exact case with the dimension equal to 3, which is a qubit with 3 possible decay rates, each one with a Krauss operator associated. And the problem with this model is that this channel has Choi rank equal to 4. And from this nice result from Kubit, Ruskai, and Smith, Choi rank equal to 4 implies that the channel is not degradable. So it would be the end of the story, but you still can simplify the model, let's say, by killing at least 1 or 2 Krauss operators, obtaining 2 subclasses of channels of MAD, single decay rate, and double decay rate, for which the degradability study is feasible. So you can find the degradable and anti-degradable regions, for which the quantum capacity can be computed with a single letter formula. But I want you to notice that we were also able to compute the quantum capacity for non-degradable regions, and which is let's say, a non-trivial thing to do in general. And we were able to do that by exploiting the composition rules we saw before and the data processing inequality for the quantum capacity. Now, I don't know if I've already ended my time. I think so. So if I don't know, there are questions, or I just switch to the next topic, you can tell me.
If there are questions, we have a little bit of time for one urgent question.
I can answer the question. I'll keep it brief. So
Okay.
the pure loss bosonic channel is a very important channel. We already heard Ludovico talk about it. And if you restrict the input space to a photon number subspace, then I believe that you induce one of your MAD channels. And I'm curious if you'd studied that in your paper. I don't know if
we are. Let's say we are working on it now. In our paper, we studied just the, let's say, finite dimensional case, and now we're trying to do the generalization derived from the bosonic case, let's say.
Okay, but the channel I'm talking about would still be finite dimensional, right?
Yeah. Okay.
Okay.
We think it is the case, but we haven't proven that yet.
All right, thanks. That's very interesting. I'll look forward to that.
All right, thanks. You can go ahead, Stefano, with your second talk.
Okay, thank you. So here instead, we'll talk about partially coherent direct sum channels and again quantum capacities. And our work started with this paper by Fukuda and Wolf, where they consider collections of channels composed in a direct sum fashion in order to obtain objects like this, where you have subchannels on the diagonal blocks and zeros on the off-diagonal blocks. Well, our construction is similar in the sense that we still have a direct sum construction, but we consider also channels where the off-diagonal blocks are non-zero, and we call these channels partially coherent direct sum channels, PCDS. One thing that can be easily seen is that a PCDS, to be a PCDS, needs a specific shape for the Krauss representation, and the shape is the block form, with where each Krauss will have 0 off-diagonal blocks. And other things that can be immediately be seen are that PCDS are closed under convex combination and closed under composition. And in particular, since identity is trivially a PCDS, they form a semi-group. And finally, we can note that to each PCDS channel phi, we can associate an entire class of PCDS given by the deep-phased PCDS, given by the composition of a PCDS phi, and a block dephasing depending on the parameter of K. And this implies that to each PCDS corresponds a direct sum channel, DS channel, when you fix the parameter K to be 0. Okay. Now, we know that degradability is a nice and useful feature to compute the quantum capacity of a quantum channel. And we found out that a PCDS is degradable if and only if also the diagonal subchannels are degradable. And in particular, the overall degrading map can be expressed just as the sum of the subchannels degrading map. Notice that the input spaces of these channels are different, so the channel is well defined. So now that we know how and when compute the quantum capacity, we were also interested in understanding if also the quantum capacity could be written in some kind of block form. We could do that by rewriting overall input states in a block form, applying the PCDS channel in this way, and then computing the entropic quantities. In this case, for instance, there is the output entropy, which in general obey this kind of inequalities. And this kind of inequality can be saturated if, as an input state, you assume to take only states with a 0 of diagonal blocks. If you take this kind of input state, you can reshuffle the coherent information in the maximization of the quantum capacity, and you will let's say divide the overall maximization into sub-maximization. And in this case, which is the 2 blocks case, you can reduce the maximization onto 2 reduced density metric space, which also implies a reduction of the number of parameters over which you will have to maximize to obtain the quantum capacity. And this is a nice feature because the computation becomes easier for, let's say, a higher dimension. And then we applied our results to basic physical noise models. The first one is the block dephasing channel we saw before for different block sizes. The second one is the MAD channels we saw in the previous talk with a single decay rate and different dimensions, system dimensions, and a combination of MAD and dephasing. And the qubit set with one block, with a qubit amplitude damping on one block and dephasing on the other block. Notice that again, we were able to compute exactly quantum capacities in non-degradable regions here, and also for the MAD, which I already saw before. And okay, I don't know if I have seconds left, but I want to mention that once you have the analysis of the quantum capacity, you will also have the analysis of the private classical capacity, and also the classical entanglement assisted capacities are available to compute. And this, I think, I ran out of time, and I'm done.
Thank you very much, Stefano.
Okay.
Thank you very much, Stefano, for your talk. Again, I'll remind the audience, of course, if you have questions, you can always ask them on the Slack. That's one of the things the Slack channel is for. So thanks again, Stefano. Actually, as we pull up the slides for our next speaker, Farzin, would you like to share your screen?
Yeah, sure. Hello.
All right. Hi. We can still have like 20 seconds before you start if we want to keep exactly on schedule.
Okay, all right.
Can you share your screen already?
Sure, I'm okay. right? I guess I have already
Great.
shared it.
Yeah, wonderful. So our next speaker is Farzin Salek. Go ahead, take it away.
Okay, thank you. I'm going to talk about multi-user distillation of common randomness and entanglement from quantum. So it's a joint group with Andreas Winter, and I'll put the archive number down here at some point. So the first test that we have studied in this work is distillation of common randomness from a mixed quantum state shared between m parti. So what is common randomness? It's actually a random variable shared by m parties, which is almost uniformly distributed. A general protocol for distillation of common randomness involves generically many interactive LOCC channels, and if NRI is the total communication rate of the ICE party, we define distillable common randomness as the achieved common randomness minus the consumed classical information. So for, I'm going to skip the important references that I have put here. So for the distillable common randomness, we construct two protocols and each yields a lower bound. Our first theorem, which generalizes a result from classical information theory known as communication for omniscience, each party measures its state with a POVM and then finally transmits non-interactively just once its classical data to all other parties, and then from Slepian-Wolf hashing function, literally from classical information theory, we find the achievable rate, and so we find the rate for the common randomness. So, but in the second protocol, actually each party applies an instrument, which in addition to that classical information, it has some quantum information. So this problem quite naturally and directly leads to the consideration of multi-party classical source coding with quantum side information at the decoder. I mean, this rate region here. So the necessary and sufficient conditions for this rate region were established in Andreas Winter's PhD thesis by successive cancellation decoding and time sharing. But for this very application, we needed to find a simultaneous decoder to realize its rate region. And actually, it took us quite some time to realize the simultaneous decoder. And finally, by using independent to universal hashing functions and a joint typicality lemma recently proved by Sen, we managed to find this simultaneous decoder, which is the main contribution of the first part of the work. The second test that we have studied is distillation of GHZ states from pure states shared between M parties. And again, we look into non-interactive protocols, and we have two lower bounds. Each lower bound comes about by making a coherent version of the protocol that we have for distillation of common randomness. While the first result, this result, reproduce a result due to Vrana and Kirstendale, the second result improves upon the first result and to our knowledge is the best current known bound. Okay, I think I'm done, but I think I finished too early.
Oh, thanks for your talk. You know, it's never bad to finish early. It leaves times for questions. So do we have any questions?
Please.
All right. Well, if not, if you do think of a question, do feel free to ask it on the Slack. And I think, well, we can thank again Farzin for your talk. Thanks a lot. And
Thank you. Thank you.
And I stop
sharing
Eyuri. Yeah, that'd be great. Wonderful. Thank you. So Eyuri, would you like to share your screen? We still have
sure, yeah.
a little bit of time before you start. But just make sure.
Can you see my slide?
I can see your PowerPoint. Oh yeah, now I can see your slide. That's perfect. Yeah.
Okay.
Yeah, you can wait a little bit.
Okay.
You know, leave everyone the time just to stretch and breathe, and so we can keep on schedule. I'll let you know when to start. All right, if you want to go ahead, the stage is yours.
Sure. Okay, so I am Eyuri Wakakuwa from the University of Electrocommunications, Japan, and I'm going to talk about one-shot state redistribution. This is a joint work with Yoshifumi Nakata and Minshu Sie. So we consider redistribution of the source state that has both classical and quantum components. Here, the classical components XYZ of the source state are depicted by the blue dots, and the quantum components ABCR are depicted by the green dots. The task is to transmit the CZ part of the source state. The sender has access to AX as a side information, and the receiver has access to BY as a side information. In addition to local operations, they can perform C bits of classical and Q bits of quantum forward communication. They can also use some amount of entanglement resource shared in advance. Note that Rx prime, Y prime, Z prime is a reference system that are inaccessible to the sender and the receiver, and that X prime, Y prime, Z prime are copies of XYZ. More formally, the problem is formulated as follows. The encoding and decoding operations are represented by CPTP maps, calligraphics E and D. Q is the Q qubit quantum message, and M is the C bit classical message. The whole procedure is represented by the diagram in the right-hand side of the slide. The source state has the classical components XYZ, 0 copies X prime, Y prime, Z prime, and the quantum components ABCR, which is assumed to be in a pure state for each value of XYZ. Our goal is to obtain the condition on the tuple C, Q, E, and E0 that is achievable within an error delta, in the sense that there exists a pair of an encoding operation E and a decoding operation D, with the communication cost C and Q, such that this trace distance condition is satisfied. And the results are as follows. First, we obtained one-shot diode and converse bounds, which are represented in terms of the smooth conditional min and max entropies. I will not explain it here in detail because the formula is a bit complicated, but let me mention that the proof is based on the partial decoupling theorem, which was proved by two of us in our previous paper. This one-shot result can then be applied to the asymptotic scenario by means of the fully quantum asymptotic equiprediction property that has been proved by Tomomichiro et al. In 2009. We obtained the inner and the outer bounds for the asymptotic rate region, which is represented by the von Neumann entropies like this. The only difference in the inner and outer bounds is that we have delta tilde here in the outer bound, which is a function of the source state psi s. So the two bounds matches if delta tilde is equal to 0, and this holds in the two cases. The first case is where there is no classical part of the side information at the decoder. And the second one is where there is no quantum part of the source state or the side information at the encoder. Various coding theorems analyzed in the previous literature can be obtained as a corollary from our hybrid redistribution theorem, both in the one-shot and the asymptotic settings. If we assume that there is no classical part of the source state, then the free quantum state redistribution theorem is obtained from our results. It is known that the free quantum state redistribution theorem is further reduced to specific cases such as state merging, free quantum Stepien-Wolf, and state splitting. So all of these results can be obtained from our hybrid redistribution theorem by reduction. On the other hand, if we assume that there is no side information at the encoder, we obtain the Stepien-Wolf theorem for hybrid source state. This family includes classical data compression with quantum side information and quantum data compression with classical side information, as well as the fully classical Stepien-Wolf theorem. Finally, by assuming that the classical part of the source state is only for the side information at the decoder, we obtain quantum state redistribution with classical side information only at the decoder. We think that investigation of the family tree in this setting would be interesting, particularly because of the non-trivial properties of the function delta tilde. For more details, please look at our paper on the archive. Thank you for your attention.
Thank you very much for your nice talk. Maybe we might have to move on to the next speaker. So again, if you have questions, feel free to ask that on the Slack. So thanks again for your talk. Marco, would you like to share your screen? Oh. Did my connection freeze?
Okay.
All right, Marco, would you like to share your screen?
Yes.
All right, wonderful. So our next speaker is Marco Fanizza. The stage is yours. Thanks.
Thank you. Okay, hi everyone. I'm Marco Fanizza from Scuola Normale Superiore, Pisa. And I will talk about our work, classical capacity of quantum Gaussian codes without a phase reference when squeezing gaps. This is joint work with Matteo Rosati, Michalis Kotiniotis, John Calzanilla from Autonomous University of Barcelona, and Vittorio Giovanetti, my supervisor. Okay, so we consider a problem of classical communication without a common phase reference. And we model the loss of phase reference in the following way. Alice's and Bob's frame differ by a phase shift, and this phase shift is constant for m uses of the transmission line, and then it is reset. Each time the phase is reset, it is extracted from the uniform distribution. Therefore, the effective channel that we consider is a channel from m modes to m modes of this form. And hat is the total photon number operator of the m modes. So the optimal strategy for this channel would be to use Fock states for the encoding, as they are left invariant by the channel, and one can easily see that they maximize the capacity. However, these kind of states cannot be easily produced. Therefore, it is interesting to see what are the optimal rates for restricted encodings with more economical states. An intuitive strategy would be to send a phase reference on one mode and use the remaining m-1 modes to communicate, for example, with coherent states. However, we can also easily see that the optimal strategies can be chosen to be covariant. That is, for any ensemble used to get a code, the same ensemble scrambled with a random interferometer gives a better rate. Now, we studied the rates for covariant coherent states encodings, and in this case, we see that for m equal 1, the channel reduces to the discrete time Poisson channel, a classical channel whose capacity is still open, and there are quite a lot of lower and upper bounds, and in particular, there is a recent one by Cherajki and Ribeiro that we use. And in fact, we compute upper and lower bounds on the coherent state optimal rate for any m, exploiting the known results for m equal 1. At high energy, we can characterize the leading order of the optimal rate, which is different from the capacity of the channel by an additive term 1/2 log E. So what about phase synchronization strategies? Here, in this case, one prepare a fixed reference state with a certain fraction of the energy. And one can find an upper bound for any strategy of this kind. And this upper bound on the rate is worse than the rate of that is obtained at high energy with a thermal ensemble of coherent states. And one can verify this suboptimality at finite energy in some cases, as we did for the m equal 2 case. So we also consider the possibility of getting advantages in the rate using squeezed coherent states. And in fact, we proved that for m equal 1, a binary encoding with vacuum and a squeezed coherent state is better than any coherent state encoding. And this is in stark contrast with what happens with phase covariant Gaussian channels where coherent states attain the optimal rate. We also conjecture that squeezing is helpful for all m based on the fact that it improves the lower bound that we can get. So I can conclude the key messages of this talk is that phase synchronization strategies are suboptimal with respect to naive coherent state encodings, and that squeezing helps in classical communication over a practically motivated non-Gaussian channel. Open question would be to find better bounds on the coherent state rates and understanding if squeezing help for m greater than 1. With this, I conclude, and thank you.
Thanks for the nice talk. Again, if you have questions, do feel free to contact the speaker over the public Slack channel. So thanks, Marco, again. Daniel, would you like to share your screen?
Yes, thanks. Okay.
All right. We still have
my slides.
Right. Yeah. Okay. Perfect. All right. Perfect. Our next speaker is Daniel Stilck Franca. So the stage is yours. Go ahead.
Thanks, Philippe. I'm going to talk about on contraction coefficients, partial orders, and approximation of capacities for quantum channels. This is joint work with Christoph Hirsche, also from Copenhagen, and Cambyse Jose from Munich. And our paper was uploaded to the archive today. You can see the archive number down there. So please cite us. Okay, so let's just quickly dissect the title, and you can find a presentation about it or a talk about it on Slack. I posted it before the session. If you are interested in hearing a bit more about this, or of course just read our paper. So the title has 3 terms. The first of them is contraction coefficients. So these can be used to quantify, in a nutshell, how noisy a quantum channel is. And we know that for any distinguishability measure, the basic requirement is that it's monotonous in quantum channels. And contraction coefficients of quantum channels try to give a fine-tuned version of data processing inequality that tells you by how much you're actually contracting. And the larger the coefficient, the noisier the channel is. That's at least intuition. So in this work, we give some new structural results for these contraction coefficients, also in the more general setting of F divergences. But we also emphasize a lot on the relative entropy, so contraction coefficients for the relative entropy, and also some new hypercontractive characterizations of strong data processing inequalities. And we show a connection to partial orders of quantum channels and contraction coefficients, which brings us to the second term in the title, which is partial orders. So one could ask the question, what is a reasonable way, what should be a reasonable definition of saying that one channel is noisier than the other? And there are different ways of formalizing this with different operational interpretation in mind. And these partial orders turn out to be very much connected to the contraction coefficients, which is one of the things we show. So in particular, we also define some new partial orders, and we put epsilons around our partial orders and the new, we put epsilons around existing partial orders and also the new partial orders we get. We prove some relations between the existing ones and our new ones. And we discussed the tensorization of various partial orders that appear in the literature, like the less noisy or the degradable, about which we just heard as well during the lightning talk. And this brings me to the last topic, because we can also use these partial orders to get capacity bounds. So as you know, capacities try to quantify how useful a channel is to transmit a certain resource. And it turns out that you can use these partial orders to obtain capacity bounds for various quantum channels. And in particular, the approximate partial orders turn out to be very useful because they lead to very simple and conceptually clear proofs of some existing bounds in the literature, like the ones based on approximately degradable channels. So we can reproduce this result by Zuta et al. In a very clean and easy way using these notions of approximate orders of quantum channels. So this is, in a nutshell, what we do in the paper. We also have some explicit results for contraction coefficients and orders in the cases of random Weyl channels and Gaussian channels as well. So yeah, check out our paper or the talk I linked on Slack. Thanks.
Thanks, Daniel, for the nice talk. All right. Again, I would suggest to make sure we keep on time, that we move on to the next speaker. Please do feel free to use Slack to ask the speakers questions. I believe there's a preference to use Slack rather than the Zoom chats, simply because it's more public and more visible, and people can still refer to the questions afterwards. All right. So, Hyejung, would you like to share your screen?
Yes. Yes, can you see the...
Can see your PowerPoint? Yeah, we can see your slide. That's perfect. All right. So our next speaker is Hyejung H. So please take it away.
Yeah, thank you. Hi, my name is Haley, and in this talk, I would like to talk about our recent work on characterizing quantum correlations of fixed dimensions. Yeah, this is an interesting topic to study because of many reasons, but most importantly, in my opinion, because it is a way to study quantitative advantages of quantum correlations with different dimensions. So to study quantum correlations, we exploit a tool called non-local games, which is a way to mathematically formulate correlations between distant parties. And I'm sorry that I don't have enough time to explain details, but in our work, we will focus on a special class of non-local games called free non-local games, where the choice of the questions for two players is not correlated. And in non-local games, advantages of different set of correlations can be captured by optimal winning probabilities. So if some set of correlation is more advantageous than others, then they can achieve a higher optimal winning probabilities. And in this talk, this last one, omega qt, fixed dimensional case, this is the one we are interested in this talk. And to compute this kind of values, we need a good mathematical characterizations for a different set of correlations. But in general, it is very hard to exactly compute this kind of values. So people have been working on approximation algorithms for this kind of values. So for this non-fixed dimensional quantum case, the MPA hierarchy provide an effective tool to approximate this values omega q. And for fixed dimensional case, there have been a few results, and some of them provide practical tools for special cases. But in general, analytical asymptotic convergence speed of these algorithms are not well studied. So in our work, what we have done is, firstly, we identified novel semi-definite constraints that can be added to the MPA hierarchy to impose dimension constraints for any fixed dimensions. And our approach was to connect this optimization problem omega qt to the quantum separability problem and employ known semi-definite programming relaxations for the quantum separability problem, which is known as DPS hierarchy. So our first result can be seen as that we combined the DPS and MPA hierarchy to derive a new hierarchy with dimension constraints. And secondly, we derived analytical bounds on the convergence speed of our new hierarchy, which led to our third result, that we gave an upper bound on the computational complexity of calculating omega qt, the optimal winning probability for the fixed dimensional quantum correlation case of two-player free games. And this computational complexity is given as this. We can estimate this omega qt within a constant additive error epsilon in time this. And where t square is the dimension of the entanglement assistant, and a is the number of possible answers, and q is the number of possible questions in a non-local game. And the important point is that this scaling is quasi-polynomial in A and polynomial in Q. And this is a big improvement compared to the best previously known result, which was exponential in both A and Q. And this is our biggest contribution. And for this regarding this second point, to derive asymptotic convergence speed of our new hierarchy, the main tool we exploited was an improved multipartite quantum definite theorem with additional linear constraints, which we also proved in our same paper. And as a fundamental step of this proof, we derived an improved version of the optical loss indistinguishability relative to quantum side information, which I believe might be of separate interest to some people. And this is the end of my talk. And please see our paper on arXiv for more details. Thank you for listening.
Thanks a lot, Haley. And sorry for mispronouncing your name earlier.
That's fine.
So I realize you also have a second talk, actually, that's following this.
Yes.
Wonderful.
Yeah, I think.
All right.
Sorry, I can't see the button. Is it okay now?
Yeah, that's yeah. Well, I
Can
think
you see? Oh, sorry, it's the same one.
Yeah.
Sorry.
Right.
How about now? Is it
That
the
looks
different
good.
one?
That looks perfect.
Yes,
It
yes.
looks
Sorry.
Right, go ahead. Go ahead. The stage is yours.
Yeah. Hi, I'm Haley again. And in this second talk, I would like to talk about our another recent paper on arXiv about resource distillation in convex Gaussian resource series. And Gaussian states and Gaussian operations are ubiquitous tools as they are easily accessible in an optical lab, but they are known to be subject to many restrictions. And the one relevant to our work is the no-go theorem for Gaussian resource distillation, which is proven in this nice paper. And it says that in any quantum resource series satisfying some reasonable assumptions, resource distillation is in general impossible if we are only allowed to use Gaussian states and Gaussian operations. And this includes all probabilistic Gaussian operations as well. And so natural question to ask will be whether we can overcome this restriction with a simple solution. So we focus on the non-convexity of Gaussian states. The set of Gaussian state is non-convex, as you can see in this picture. If you mixed two Gaussian states, the outcome state is in general not Gaussian. So we wondered whether this kind of classical mixing could help resource distillations. So to study this, we introduced the notion of convex Gaussian resource series in our work, in our paper, which is a special type of quantum resource theories defined like this. So now we have two resources, some resource F, and the non-Gaussianity. And the free states are given by the convex hull of free Gaussian state. So in the picture, it would look like this. So it's the convex hull of the intersection between the original free state of this resource F and the Gaussian state, which are the free states of this non-Gaussianity. And the allowed operations are given by two elements. First, appending a free state, rho, and applying free Gaussian operations condition on the measurement outcome on another mode. So it's a conditional free Gaussian operations. So for example, in Gaussian entanglement theory, the resources will be entanglement and non-Gaussianity, and the free state will be given by the convex hull of separable Gaussian states. And the allowed operations will be appending a Gaussian separable state and applying conditional Gaussian LCC operations. And so with this, in our paper, we show that we fully characterize the new restriction on resource distillation in convex Gaussian resource series, and we show that this new restriction is more relaxed than the one for the Gaussian case. So even though there is still restriction, some limited kind of resource distillation becomes possible in this convex Gaussian resource theory regimes. And to show that, we define a new resource measure kappa tilde for the convex hull of Gaussian states so that we can apply it to even non-Gaussian convex mixtures of Gaussian states. And it is the convex roof extension of Gaussian resource measure kappa defined in this paper. And this is the theorem we showed. And what it says is that if we have some state rho, which is a mixture of Gaussian states, it could be continuous mixture as well. And if we denote the most resourceful state among these elements as rho max G, and the theorem says if we have another convex mixture of Gaussian states, tau, which is more resourceful than this most resourceful element in rho, with respect to the newly defined measure kappa tilde, then this state transformation is impossible only using allowed operation, even though we have many copies of the initial state. And this is the restriction part, but this theorem doesn't exclude the case when this tau is more resourceful than rho, but less resourceful than rho G max. So this kind of state transformation could be possible, and it's not forbidden by this theorem. So as our second result, we show that this kind of state transformation is possible by providing explicit examples of squeezing and entanglement distillation protocols. So we show that limited kind of resource distillation becomes possible if you're allowed to use convex mixtures of Gaussian states and conditional Gaussian operations. And particularly, we show that this upper bound can be reached in some special cases with explicit examples. So we can extract the most resourceful state from the initial state in convex Gaussian resource theories. And this is the end of my talk. Thank you for listening.
Thank you very much, Haley. And I suggest that we all unmute ourselves and quickly thank all the speakers of this session. There were some very nice, interesting talks.
Thank you.
All right. So thanks for attending this lightning talk session. I believe we have a 15-minute break now, and we'll reconvene.